Have you ever stopped to wonder what would happen if you ran an electric motor backwards? It's such a simple question, right? But the answer is so profound that it literally powers our entire civilization. So let's dive into this amazing two-way relationship between motion and electricity.
Here's our roadmap. We're going to see how this one big reversal leads us from a basic physics idea to actually making electricity from motion, then to mastering that electricity with a really clever device, and finally, to seeing how this whole system powers an entire nation.
First up, the big reversal. This is where we get into the beautiful symmetry at the very heart of electromagnetism, this idea that motion and electricity can just swap places. Okay, so back to that big question. We all know a motor takes in electricity to create motion. But what if you flip that? What if you provide the motion first? What do you get? Well, the answer is electricity. You've just created a generator.
You can see right here how electromagnetism is a perfect two-way street. On the left, you've got the motor effect. You put electricity in, you get motion out. Think of an electric car or even a loudspeaker. But on the right, you have the generator effect, which does the exact opposite. You put motion in and you get electricity out. It's the same fundamental principle, just running in reverse.
And this brings us to the official definition, the generator effect. You might also hear it called electromagnetic induction. Basically says that when you move a wire through a magnetic field, a voltage gets created, or induced. And that word induced is so important. It means the electricity appears almost like magic, with no direct contact. The magnetic field itself is literally pushing the electrons along the wire.
All right, so we've got the principle down. Now for the fun part. Let's move on and see how we actually put this brilliant idea to work to generate the power we use every single day.
To make it happen, you only need three things. First, a conductor, like a simple copper wire. Second, a magnetic field. And third, this is the crucial one, relative motion between the two. You can move the wire, or you can move the magnet. It honestly doesn't matter which, as long as something is moving. The moment the movement stops, the electricity stops too.
Ah, but there's a catch, and its name is Lenz's law. What this means is, as you try to move that wire through the magnetic field to make electricity, the current you create generates its own magnetic field that actually pushes back against you. You have to fight it. And this is just a beautiful illustration of the conservation of energy. The physical work you are doing, your effort, is what gets converted into electrical energy. There really is no such thing as a free lunch in physics.
Now, depending on how you build your generator, you can get two different kinds of electricity. If you use simple slip rings, you get an alternating current, or AC. See that smooth, flowing sine wave? That's the kind of power that comes from the sockets in your wall. But if you use a clever little device called a split ring commutator, it flips the connection every half turn, and you get a bumpy but direct current, DC. One tiny mechanical change gives you a totally different electrical output.
You know, for a perfect real-world example of this whole reversal thing, you don't have to look any further than a microphone. A loudspeaker uses the motor effects to turn electricity into sound. A microphone? It does the precise opposite.
So check this out. When you speak, the sound waves from your voice make a tiny diaphragm vibrate back and forth. Attached to that is a little coil of wire sitting inside a magnetic field. As that coil moves with the vibrations, the generator effect kicks in and induces an alternating current in the wire, an electrical signal that is a perfect replica of the sound of your voice.
Okay, so we can generate electricity. Awesome. But how do we control it? That brings us to our third section, the voltage changer. This is where we meet a device that uses the generator effect in a way that is just pure genius, the transformer.
Now, this is the single most important thing to get about a transformer. Its job is to change the voltage of a current. And, this is critical, it only works with alternating current, AC. Why? Because AC is always changing, so it creates a constantly changing magnetic field. You need that change to induce a current. A steady DC current creates a steady magnetic field, which does nothing.
Transformers basically come in two flavors. A step-up transformer has more coils of wire on the output side than the input, and just like its name says, it increases or steps up the voltage. A step-down transformer has fewer coils on the output, so it decreases the voltage. It's a beautifully simple design.
And the math behind it? It's almost too simple to be true. The ratio of the number of turns of wire on the first coil to the second coil is exactly the same as the ratio of the voltages. Let's see it in action.
So let's run the numbers.
Imagine you've got a transformer with 200 turns on the input coil and 2,000 on the output. That's a 1:10 ratio. If you feed it 25 volts, the equation tells you you're going to get 250 volts out. 10 times the turns gives you 10 times the voltage. Simple as that.
But hang on. Remember Lenz's law? No free lunch? In a perfect world, the power you put into a transformer has to equal the power you get out. And since power is just voltage times current, if you step the voltage up by 10 times, the current has to step down by 10 times to keep everything perfectly balanced. Energy is always, always conserved.
And this inverse relationship, this trade-off between voltage and current, it's not just some neat physics trick. It is the absolute key to powering our entire modern world. Let's see how.
Okay, so here's the fundamental problem. When you send electricity down a long wire, some of that energy gets lost along the way. It just turns into useless heat because every wire has at least a little bit of electrical resistance.
And the physics behind that loss is all in this little equation. The power you lose is equal to the current squared times the resistance. Now look closely. The real villain here isn't the resistance, it's the current, I. Because it's squared, its effect is massive. Even a small current can cause huge energy losses.
Which leads to the massive engineering challenge, right? How in the world can you get electricity from a power station to a city hundreds of miles away without all of it just fizzling out into heat before it gets there?
Well, the solution is just ingenious, and it's all about transformers. Here's the plan. First, at the power station, you use a massive step-up transformer to crank the voltage up to an insane 400,000 volts. Because power is conserved, that crushes the current down to a tiny, tiny value. With a super low current, those I squared R heat losses become almost nothing, so the electricity can travel for miles super efficiently. Then, right near your town, step-down transformers bring the voltage all the way back down to a safe level for your home.
So let's just recap that whole amazing journey. It all starts with a simple fact. Magnetic fields exist. Then we learn that electric currents create their own magnetic fields. Put that current inside another field and you get the motor effect, you get motion. And finally, if you just reverse that whole process, put motion into a magnetic field, you get the generator effect. A perfect, beautiful, logical chain.
Which leaves us with one last big thought. The discovery that electricity and magnetism weren't two different things, but were actually two sides of the same coin, electromagnetism. That was one of the biggest leaps in human history. It just makes you wonder, what other invisible forces of nature are out there, just waiting for us to find their hidden connection?